In this tutorial, we learn how to write a polynomial function in its factored form. We also learn how to solve a polynomial equation. Now, this tutorial comes in several parts. In each part, we work through an example, the first of which is shown here. We're given f of x, which equals to x cubed minus 2x squared minus 5x plus 6, and we're asked to 1, write f of x in its factored form, and secondly, we need to solve x cubed minus 2x squared minus 5x plus 6 equals to 0. So I'll start by moving the question to the side, like so. Now the function that we're dealing with here is f of x, which equals to x cubed minus 2x squared minus 5x plus 6. And so we'll start with question 1, that is, write f of x in its factored form. So I'll just put a little 1 here. To write a polynomial in its factored form, we need its zeros, also known as roots. And when it comes to cubics or quartics or quintics and beyond, there's no equivalent of the quadratic formula, meaning there's no nice formula that's just going to give us all the zeros. But luckily for us, there are plenty of little tricks to find those zeros. Now, looking at the function that we have here, we notice that the leading coefficient, that's the number multiplying the highest power of x, is 1. Indeed, we have 1x cubed. When that happens, we can often find the zeros, or at least one zero of our function, by looking at the factors of the constant term inside our polynomial. So in this case, those would be the factors of 6. Now, the factors of 6 are 1, 2, 3, and 6. And in fact, we can go further than that and say that the factors of 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Careful, it's important to remember to consider the plus or minus possibility here. So we can see from this list that we have 2, 4, 6, 8 potential zeros for our function. Now, to figure out whether or not one of these factors is a zero of f of x, we're left with trial and error. Here's what I mean. Let's try and see whether or not negative 1 is a zero of f of x. So to be clear here, I'm going to go ahead and calculate f of negative 1 and see if it's equal to 0. To do that, I'm going to use Horner's algorithm, which I present in a table, something looking like this. At the top of this table, I need to write all of the coefficients of f of x. So those would be 1, negative 2, negative 5, and 6. So I write those at the top of the table, 1, negative 2, negative 5, and 6. Now, I want to calculate f of negative 1, so I write this negative 1 on the upper left-hand side of the table, like so. Now I carry down the leading coefficient to the bottom of the table, and now I can get started. 1 times negative 1 equals to negative 1. I add this negative 1 to the negative 2 above it. That's negative 2 plus negative 1, which equals to negative 3. Now, negative 3 times negative 1 equals to 3. I add this 3 to the negative 5 directly above it, so that's negative 5 plus 3, which equals to negative 2. Now, negative 2 times negative 1 equals to 2. I add this 2 to the 6 above it, that's 6 plus 2, which equals to 8. This 8 tells us that f of negative 1 is equal to 8. In other words, it's not equal to 0. So negative 1 definitely isn't a zero of this polynomial. So we carry on. Let's go ahead and try f of 1. And again, I use Horner's algorithm in a table, like so, at the top of which I rewrite the coefficients, so those were 1, negative 2, negative 5, and 6. And this time I'm evaluating f of x when x equals to 1, so I write 1 in the upper left-hand side of the table. I carry down the leading coefficient, that's 1, and now 1 times 1 equals to 1, and I add this 1 to the negative 2 above it, so that's negative 2 plus 1, which equals to negative 1. Negative 1 times 1 equals to negative 1, and I add this negative 1 to the negative 5 above it, which equals to negative 6. I carry on negative 6 times 1, which equals to negative 6, and I add this negative 6 to the 6 directly above it, so that's 6 plus negative 6, which equals to 0. And this 0 tells us that 1 is a zero of this polynomial. In other words, 1 is a root. So f of 1 equals to 0. Now, since f of 1 equals to 0, the factor theorem tells us that the linear x minus 1 is a factor of f of x. In other words, we can already state that f of x equals to x minus 1 times something. And luckily for us, that something can be obtained simply by reading these coefficients that I'm underlining in green at the bottom of the table. Indeed, these numbers 1, -1, and -6 are the coefficients of what we call the quotient polynomial, usually referred to with a capital Q of x, which in this case will be a quadratic, which is x squared minus x minus 6. Notice that this quadratic's coefficients are nothing more than the numbers obtained at the bottom of this table. So going back to f of x, I can write f of x equals to x minus 1 times q of x, which is x squared minus x minus 6. And now to finish writing f of x in its factored form, all we have to do is write this quadratic in its factored form. And we know how to do that. Indeed, we can write that x squared minus x minus 6 is equal to x minus 3 times x plus 2. Using that result, we can now write f of x in its fully factored form as f of x equals to x minus 1 times x minus 3 times x plus 2. And that's the answer. Now that we've written f of x in its factored form, we can move on to question 2. Remember, we need to solve the equation x cubed minus 2x squared minus 5x plus 6 equals to 0. In other words, we want to solve f of x equals to 0. Well, luckily for us, now that we've written f of x in its factored form, that's quite simple. Indeed, f of x will equal to 0 if either one of its linear factors equals to 0. In other words, if x minus 1 equals to 0, which would lead to x equals to 1, or if x minus 3 equals to 0, which would lead to x equals to 3. And finally, if x plus 2 equals to 0, which would lead to x equals to -2. And those are the three solutions to the equation. And there we have it. That's the end of this first example.